Be left with, let's see, pull that out of there, we get a 2y. Pull that out of here, we get plus sine y. Still good? Final step. Divide both sides by what's in that parentheses. If I divide the left side and right side, all right, if I divide this by this, and divide this by that, it'll go away over here. And then I'll have dy dx by itself, won't I? So I'll have 3x squared minus 1 over 2y plus sine y equals dy dx. Questions? Again, to find the slope of the tangent line, you will have to provide me with what? Both x and y. And it makes sense. Look at the curve, right? The curve looks like this, something like that. So if I want to know the slope of the tangent line here, it's going to be different than the slope of the tangent line there, right? Here and here. Those have same x coordinates, but they have different y coordinates. So now, finding an actual point, that's a little hard to do. Like this hard, I would have to give you the point. So on a test, if I said, hey, find the slope of the tangent line for this curve, right? At a point, I would give you the point, right? Once I give you the point, then you'd be able to find the slope, right? Then you go back to that formula, it just doesn't go away, right? Y minus y1 equals m times x minus x1. Right? Okay. Let's look at another one. Cosine xy equals 1 minus sine y. Cosine of xy equals 1 minus sine y. Let's look at that graph. Same questions here. Find dy dx. Let's look at the graph, okay? Let's see what the graph of that looks like. All the points that satisfy that equation. You ready? Here it is. Yeah. Whoa, right? That's weird, okay? It's definitely not a function, right? Fails a vertical line test. But yeah, you make art. So look, I mean, if you could tell me a point, I could find the slope of the tangent line, right? But you'd have to give me the point. Right? You couldn't just give me the x coordinate. I'd have to know the exact point. But if you do that, if you give me the point, I should be able to calculate the slope. But I need to take the derivative of that. And I'm going to do it with respect to x, right? Implicit. Here we go. d dx of cosine of xy equals d dx of 1 minus sine y. Implicit differentiation is about to happen. Over here, what am I going to do? Chain, right? So I'm going to take derivative of the outer function first, this, and then once I get inside, I'm going to have to do a product rule, right? That is a product. So let's see if we can do it. How much can we do at one time? Derivative of cosine of this is negative sine of the x times the y, right? Times, right? Chain rule, times. Now the derivative of inside. Here's your product rule. So, right? Yeah. So I'm going to need a set of parentheses here, because when I do a product rule, I get two terms. So I'm going to do a set of parentheses. All right, let's see if you can do this derivative. Product rule. What's derivative of the first one? dx dx, which is 1. Times y. Okay, plus, now the derivative of the second one. dy dx times x. Good. Okay, are we done over here?
No.
On the left side?
Yes.
Yes. Because we did the derivative cosine, boom, got it. And then we took derivative what's inside, got it, we're done. Equals. On the right, these two are separated by subtraction, right? So derivative of 1, 0, minus, okay, derivative of sine of y. Cosine of y, dy dx times dy dx. That's chain rule, isn't it? You're taking derivative, forget the minus, take derivative of sine of something, it's cosine of it. And then the derivative of what's inside. Derivative of y with respect to x, dy dx. Yeah? Okay. So that's what we've got, right? I need to get my dy dx's together. And I have a little bit of an issue on the left side. Do you see the issue on the left side? The dy dx is inside that set of parentheses. You can't just pull it out of there. So in order to get this dy dx free from this parenthesis, you're going to have to take this entire thing and distribute it through. All right? Yeah, it sucks, but that's what you're going to have to do. So negative sine of xy times this first term. This is really just y, right? So I just need to multiply y times that. Won't that give me negative y sine of xy? Yeah, sine of xy. Is that not the first multiplication? Here to here, right? Now, here to here. Still have a minus? I'll have a dy dx. I'll have an x. I'll have the sine xy. The order of these don't matter, okay? This is multiplication. The order doesn't matter how you put these, right? I just need to make sure that I multiply this times those two things. All those things need to be multiplied together. It's a minus because this was negative and this was plus, right? Is that clear on that second multiplication through? Okay, the right side is, there's nothing you need to do on the right side. This is just equals negative cosine. Well, God, this thing's in my way. That's all right, I'm just going to rewrite the whole thing. Okay, that's where I am, right? What? Yeah, the only thing I did there is that, I just got rid of that 0 in front. We good? All right, everything that has dy dx is going to go to one side. So this entire thing, that whole thing, and this whole thing, right, need to be on the same side of the equation. So I can either move these both to the left or both to the right. My choice, your choice. I am going to take this one that way. And that will leave this one alone, won't it? Okay. So I'm going to have y, negative y, sine xy equals, when I move this over, it's going to become plus, isn't it? Because it's a minus over here. So I'm going to put it first because this one's negative, isn't it? Okay. Are we all okay with this? Yeah, go ahead. What? Okay, so you got it? You're good? Okay. Yeah, the 0's gone. I just wanted to put it there because the derivative of 1 becomes 0. I just want to make sure you understood that I did account for that 1. Yeah, I think now they both have dy dx. I can factor it out, can't I? So negative y sine of xy equals, how are we doing on time? Dy dx x sine xy minus cosine y. That's what it looks like if I pull the dy dx out of both of them. Final step, divide through by what's in this parentheses on both sides. So my final result will be negative y sine xy over x sine xy minus cosine y equals dy dx. No, I don't want to go there. All right. Questions? That's our answer? I better close that graph here, get rid of it. Let me see if I have any other examples there. No.
So is this like a raw derivative, or is there more we can do to this?
Nope, that's. I mean, there might be algebra you can do in here to clean this up. There might be some, but my goal is just to get dy dx by itself. Like, you can't cancel these, right? Because you would have to have one of those in all three.
Right.
How about this one? Find equation of tangent line to the curve x cubed plus y cubed equals 2 at the point 1, 2. Let's take a look at this curve. I'm going to graph it for us first. X cubed plus y cubed, cubed, equals 2. There's the graph. There's the graph. And I want to know at, wait a minute, 1, 2, the heck? If I plug in 1 there, 1 cubed plus 1 cubed is 2. Did I type the graph in? Oh, no. Why is that point not on there? Oh, 1, 1. Sorry, 1, 1. I apologize, 1, 1. At 1, 1. I know what I did. That point's on there, yes? Yeah. You have to be careful. I just did what you shouldn't do. This is x, this is y, right? If I plug x here and y here, 1 and 1, I get 2, right? So if I want to find the equation tangent line, I need dy dx, don't I? I need the derivative. So let's differentiate this with respect to x. d dx, x cubed plus y cubed equals d dx of 2. All right, this right here is going to be 3x squared plus 3y squared times dy dx equals 0. Take a moment, agree or disagree with me there. Ask a question if you're not sure where that came from. Yes?
Are we doing with respect to x versus respect to y?
Because if you go back and look at our notes, when we first defined f prime of x, the slope of the tangent line, we said another notation for that is dy dx. And that comes from the idea of if we want to know the slope of a line connecting 2 points, it's always going to be the change in y over the change in x, rise over run. We want to know this divided by this, not the other way around. We don't want to know run over rise, right? So if I want to know dy dx, I'm going to need to differentiate with respect to x. And that's why I come in here with dx on the bottom. Okay? So no questions here? Now, what we've been doing prior to this, right, like in this example, we then went and solved for dy dx, right? I went and solved for it. You don't need to do that in this problem. Well, you do, but you don't need to go do it algebraically like we did here, because I actually have a point, don't I? I'm given the point 1, 1. So at this point, I can say at the point 1, 1, right, that's x, that's y, we get this. 3 times 1 squared plus 3 times 1 squared times dy dx equals 0. See, I'm just going to replace all my x's with 1s, all my y's with 1s, and then I can just solve for dy dx this way. You see what I'm doing? So this is just 3 plus 3 dy dx equals 0. And move the 3 to the other side, you get 3 dy dx equals negative 3, and then divide both sides by 3, and you get dy dx is what? Negative 1. Do you see that when you're given a point, you can actually find your dy dx right after you do the implicit, right after this step. Plug in all your x and y's in, and then go get the number. Now, I'm not done, right? No, that's just the slope of the tangent line, right? I want the equation of the tangent line. So I'm going to go back to my good old formula, y minus y1 equals m times x minus x1, this one, right? This becomes y minus 1 equals negative 1 times x minus 1. I'm using this is x1, this is y1, right? And then that's my slope. I hope I've beat this into you enough. Have I beat that into you enough? Let's check our answer. I'm going to graph that line. Y minus 1 equals negative 1 times x minus 1. There. See, it's the line that hits there. We good? Same question, same problem, okay, but I have a different question. Find what does that mean? Find the second derivative. How do we find the second derivative? Right, we know how to find the first derivative, right? But how do we find the second derivative? We have to take the derivative of the first derivative, right? That's what we normally do. Find the derivative, then take derivative of that. That will give you the second derivative. This is going to be a little different. So first thing I'm going to do is I'm going to take the derivative, which with respect to x, which we've already done, right? So we know that we get 3x squared plus 3y squared times dy dx equals 0. We're all okay up to this point? That was just me doing the derivative with respect to x. What I'm going to do now is I'm going to do it again. I'm going to take the derivative with respect to x again on both sides of this equation. It's going to be weird, but just do it, all right? So I'm going to take the derivative with respect to x on the left side. Equals the derivative with respect to x of the right side. Yes?
For dy dx, can we just plug in the equation from before? So
for dy dx,
the solved version of it?
oh, could you go solve this for dy dx and put that in there?
Yes, sir.
You could, but sometimes that's going to be a lot more work than you should do. Okay. But yes, you could. I'm going to leave it like that for now, though. Are we okay with that? I'm going to take the derivative. Here we go. So when I take derivative, I have a plus sign here, right? So I can do these separately. What's derivative of 3x squared with respect to x? 6x, right? The good old-fashioned, right? That's the good old-fashioned derivative right there. Plus, now here. Who sees it? It's what? It's a product rule. You have to do a product rule right there, right? You're about to differentiate the product of two things. 3y squared and dy dx, right? Those two things are being multiplied. So apply your product rule here. What's the derivative of the first piece? Good. 6y dy dx, right? Times product rule. Derivative of this one times dy dx. Plus, now, what's the derivative of the derivative? The second derivative, right? That's what we're actually solving for, isn't it? That's what that means. So when I take the derivative of that derivative, this is where I get the d square y dx squared. That's just notation that means the second derivative. I just took the derivative of that derivative, right? Now what? Multiply times what? 3y squared. That's me finishing off the product rule, isn't it? Do y'all see the product rule? Derivative of this times that plus the derivative of that times this. This 6x was separate because that was addition. I could do it separately. Okay, done with the left side? What's the derivative of 0? 0. That's still nice, isn't it? There you go. You see the second derivative in there? You can solve for that, can't you? You could get that by itself right now. One thing I do want to stress here, this is not the second derivative. That is the first derivative squared. Totally different things. So if you wanted to rewrite this, you could rewrite it dy dx squared, and everyone would understand that you mean you're taking the first derivative times itself, as opposed to taking the second derivative, which is something else, yeah? So I'm going to get this by itself. Second derivative times 3y squared equals, I'm going to move all this crap to the other side. Negative 6x minus 6y dy dx squared. You'll see what I did? Left this alone, took everything over here to the other side of the equation, which made them both negative. Last step, divide by 3y squared. So take this, divide by 3y squared, and you have what the second derivative is. Notice that in order to calculate the second derivative, you're going to need to be able to give me x and y, right, the point on the curve, and you're going to have to be able to give me the derivative at that point as well, the first derivative squared. Well, how do you get the first derivative? You would get it from here, right? So you're asking a second ago, could we have just solved for this? Yes, we could have solved, what's dy dx if we solve for it here? You get negative x squared over y squared. So if you move this over, divide by 3y squared, you'll get this, right? If you wanted to, you don't have to. If you wanted to, you could take that answer right there and plug it in right there and square it. And that would be an answer for the second derivative that would not have the first derivative in it. It would just have x's and y's. All right, how are you feeling? Yeah? The homework for this, we're not going yet. The homework for this, pretty sure you should be able to handle it, okay? 2.6. In other words, with what we've developed today, you should be able to handle most of that exercise, or most of that assignment. I'll look at it later and see if there's anything. I forgot my textbook, so I'm pretty sure you can at least get it going. We are behind, right? We are behind in this class right now. So this last 9 minutes, I'm going to use this last 9 minutes for something, all right? Should I do another example? Are you okay? What's up? Implicit differentiation is extremely powerful. I could not overstate how important this method for taking derivatives is, because it works for anything. Any equation you could ever come up with, this works for. So I'm going to look at an example. You may have seen this before. Anyone ever seen that equation before? Where have you seen it? Chemistry? You know what it's called?
Boyle's law?
Hmm?
Is that Boyle's?
I don't think it's Boyle's law. I don't think it is. I'm not a chemistry person.
It's pressure.
I thought it was the ideal gas law.
Yes, it is.
I think it's called the ideal gas law. Either way, it's an equation from chemistry. And what this has to do with is if you have a container and you have some gas inside this container, all right? So this is a closed container. These things are all connected through this equation. P here stands for pressure. So the pressure in this container times the volume. So if you take the pressure in the container, you multiply it times the volume of the container, then that will always be equal to N times R times capital T, which is temperature. Now, one of these is a constant, Avogadro's number, and the other one is the number of moles or something like that. This is moles. This is like, I don't know if that's Avogadro's number. It's a different number. It's a different constant, though. Yeah, it doesn't matter. This right here, see it from a math perspective, that's a constant. That's all I care about, okay? This is a variable, this is a variable, that's a variable. That never changes, all right? So, you're shaking your head, you all right?
Yeah, I forgot about this from last semester.
Yeah, don't worry. I mean, the point of this is that this relationship that we have between pressure, volume, and temperature is well, that's the relationship. So if I increase the pressure, right? If I increase the pressure and I keep the volume the same, then what's going to happen over here? Temperature is going to have to go up, right? More pressure, temperature gets higher. If I release the pressure, right? Pressure goes down, volume stays the same, temperature is going to have to drop as well. Right? And that's we have this balance, right? If I decrease the volume, right, then what happens here? Decrease in temperature, right? So this balance has to be maintained. So what we can do in calculus is we can take any equation, doesn't matter where it comes from, chemistry, physics, biology, any equation that exists out there, and what we can do with it is we can ask, how are these variables related to one another if you start to change one of them a little bit, right? Like, what if I make a little bit of a nudge in the V? How does that affect everything else, right? Or if I nudge the pressure a little bit, how does everything else change? Make sense? So let me ask this question. I want to know what is dp d Do y'all hear water running? Wait, shh. I swear there's water running. Wait. There's water running. But there's no bathroom right here. Isn't there a lab up there? I think there's a lab up there. Okay, who cares? So there. So what that's saying is, look, if you make a little nudge in the temperature, right? How's the pressure impacted? Right? That's what that's saying. When you make a little change in temperature, tell me what the pressure does. Well, to do that, I have to take this and I have to do implicit differentiation, right? And I have to do the derivative with respect to what on both sides?
T.
Capital T. Why? Because I want to know dp dt, right? So I'm going to need to do d capital T on the left side and d capital T, oops, I curled that T, on the right side. Okay? On the left side, what do you see? Product rule, right? Because these are both variables, aren't they? Pressure and volume are not fixed. They're variables. They can change. So when I take the derivative on the left, I have to do derivative of the first one. What's the derivative of the first one? dp dt, right? Times v plus dv dt times p. Okay, that's the derivative of the left side. On the right side, this is a constant. When we take a derivative where the constant is attached to a function, the constant comes for the ride, right? So don't tell me the derivative that's 0. If that wasn't there, yes, derivative is 0. But because the t's there, it comes for the ride. So equals what? nr times, now, what's the derivative of the t with respect to t? 1. You see? Yes, yes? What were we asked for? This? It's right there, right? Why did I use lowercase t? I'm sorry. I know why, because next class, all we're doing is pretty much time. Time will be our thing that's changing. We're going to be nudging time and seeing what happens to something. Like some physical situation, right? You're blowing up a balloon. Nudge time, see what happens. All right, yes? So I can solve this. dp dt times v equals nr minus dv dt times p. So I just move this over, right? With this nr times 1. And now finally I'm going to divide by v. So dp dt equals nr minus dv dt times p. The whole thing divided by v. And now we have a formula that will tell me if I nudge the temperature a little bit, right? If I nudge the temperature a little bit, it'll tell me how much the pressure changes. But in order to do that, you're going to have to give me a lot of information. You're going to have to tell me the pressure. When you do the nudge, tell me what the pressure was right then. Tell me what the volume was right then. And this one, you're going to also have to tell me how much the volume was changing. When you nudge, you have to know how much the volume changes. So we're gonna look at some problems like this next class. You can start packing up. This formula, well, yeah, I won't talk about it. Y'all have a good weekend. Do your homework for implicit. Do your chain rule worksheet. All right. The chain rule, is due next week, a week from today. A week from today. Let me turn off my camera real quick. If you did not pick up this worksheet, it's due next week. Everyone got that?